Welcome to my channel. In this video, we are going to show you how to calculate the roots of a polynomial of order 3. And we already know how to calculate polynomial of order 2 using the general formula, such as the completing the square method. But in this case, there is a general formula that we are going to apply to solve this particular problem. And that formula is not too common. So that's why we want to show you how to compute the roots of this kind of equation. Now what we have here is the polynomial. We can see the roots: lambda cube minus 7 squared plus 14 lambda minus 8 equal to 0. What we need to do is to write down the parameters a, b, c, which are, for a, the coefficients of lambda squared, for b, the coefficients of lambda, and finally for c, the value of minus 8, which is here. When we are solving, we construct q, which is equal to 3b minus a squared all over 9. Then by the time we insert the parameters into this, we'll get this expression. Now it is advisable to always leave this decimal up to 6 or 7, so that at the end our result will be very accurate. So after constructing q, the next thing is to construct r. R, we use this formula. Now this formula will make use of 9ab minus 27c minus 2a cubed all over 54. When we insert all these values, we'll get up to this decimal. You can see we are leaving it up to 7 decimal so that our result will be very accurate. Then also we construct d. Our d is coming from q and r that we generated earlier. Remember, our q is minus 0.777778 raised by 3, and our r is this newly generated value, which is this value here. We'll get it here. Once we construct this, then we'll move to the next stage. Then the value of d constructed is given as this, but we notice that when you're finding the square root of minus 1 or any negative number, it must have a complex number which resulted to this. Then we take the square root of this inner expression, which gives us this. Then the next thing is to construct s. Our s is equal to r plus d raised to power 1 over 3. And recall that our r is equal to this expression. Our d is this new expression here, which is inserted here, raised by 1 over 3. And if you notice, our s is a complex number. When you are solving a complex number, it is usually preferred to take the cube root. When you are solving a complex number and you want to take the cube root of a complex number, it is usually preferred to convert from this usual form to the polar form, which is this, where our r is the square root of z1 plus z2 all square roots. And by the time you insert the value of r, z1 and z2, we'll get this value as our r. So the next thing we'll do is to construct the value of theta. Our theta is given as arctan z1 all over z2, which is equal to this expression. Remember, we have our z1. So we construct our theta, which is equal to z2 all over z1. I think there was a mistake in the previous one, which was z1, z2. So it's now z2 all over z1. Then we have this expression. And theta becomes 57.319. Now, sometimes the value of theta can be negative. And when it is so, you must add 180 to it to make it positive. But in this case, we're having theta equal to a positive value. Now, recall that our s is equal to z1 plus iz2 raised by 1 over 3, which is the cube root of this, is now equal to this. It is preferable and easier to solve the cube root of a complex number in this form. So when it is in this form, to take the cube roots, we take, which is exactly this expression, we just take the cube of the value of r, the cube root of the value of r, then divide it theta by 3. And when you take the cube root of this value, you get this other one. You divide the angle by 3, you get this value. And that will be the value of s, which is this. Now to get our t is just the complex conjugate of what? S. And in so doing, you just change your negative, this value from positive to negative to get the value of what? T, which is complex conjugate. So the next thing we'll do is to construct the roots. In constructing the roots, we'll get these values. We'll get these values, and from here, recall that our a is equal to 7. And for the first root, this is what we use, s plus t minus a all over 3, where a is equal to what? 7. Now, when you fix in the value of s plus t, remember it's a complex number, then we extract this value, which is common. Our r is common, the remaining this and this, then minus 7 all over 3. At the end of the day, recall this value remains here. If you simplify this one, if you convert from this expression to the cosine form, it gives you 2 times this expression. Then minus and minus changes to plus, which is 7 over 3. At the end of the day, we'll get this expression. So if you recall what I said earlier on, where our answer, if we don't convert it to, if we don't express it in higher values of decimal, that's up to 7 or 8 decimal, our answer might be approximately not too correct. So, but in this case, you can see our final answer is 4.0000, which tells us that the answer is exactly 4. Then for the second root, we use this formula. And for this formula, we just substitute and we'll get these expressions. And once we get these expressions, then we can easily determine the roots of the second root. And by the time we're fixing the values, our second root is equal to approximately 1. This one tells us that our answer is approximately 1. For the third root, the formula is similar to that for the second one, just that this one is minus. Then we'll still substitute all these values and we get 1.9999. And seeing this one, we immediately tell that our answer is approximately 2. So the 3 roots that we have determined is 4, 1, and 2. So by the time you multiply this 4, 1, and 2, that will give you the last term of that quadratic polynomial. Now this one is just an extra, where our s minus t equal to r, I theta all over this is exactly equal to r 2 times I sine theta. So by the time you multiply I root 3 all over 2 multiplied by this, it gives you this value. Thank you, and subscribe to my channel for more videos like this. Thank you.